Is the equation dimensional? Is the values nu and y and phi, do they have units? Phi does. Y also does, right? It's just a length, right? Also, kinematic viscosity has units, right? So what is the unit of theta? It's 1 over length, right? I mean, same thing as alpha. It's a non-dimensional scaling divided by dx, right? Remember the definition of both theta and alpha, right? Okay, so this is theta. Y, of course, is L, and nu, what is nu? L squared over T, right? How about phi? It's velocity integrated over length. L squared over T, yes. Okay, now I can write my phi as a function of what? If you just look at this equation. Oh, sorry, I need boundary conditions. So this differential equation doesn't uniquely define the solution, right? I also need boundary conditions to uniquely define the solution. How many boundary conditions do I need for this third order equation? 3, right? For first order equation, I need 1 boundary condition. Second order, I need 2. Third order, I need 3. So what do you think are the appropriate boundary conditions? Velocity, which is d phi d what? dy, right? At y equal to 0 is equal to 0, right? We already said we defined actually phi at y equal to 0 to be 0, right? It's a streamline, right? And what else? Second order derivative stream function is going to be 0, so which means like you want, right? That I guess wouldn't really work because 0 is going to be a solution for that one. So phi equal to 0 would be a perfect solution for this equation and these 2 boundary conditions and the boundary condition you proposed, right? So you end up having a system of differential equation and boundary conditions that are singular, which you can test by just plugging a 0 solution and say, oh, they are all satisfied, which means I have a, yeah. Yes, that works. So d phi dy at y equal to infinity, let's say, or y equal to something sufficiently large is equal to ue. All right. Now, this is a full set of equation and boundary conditions that can uniquely define the phi. So phi should be a function of what? And let me also write ue here. Ue here is L over T, right? So phi should be a function of what? Y for sure, right? Okay. And well, here it looks like it's a function of theta and nu, but like you can just divide both sides by theta or by nu. So it should only be a function of nu over theta or theta over nu, right? Okay. And what else? We also have ue, right? So okay. So we have phi as a function of y and nu over theta and ue. L and T, right? So 1, right? That's how the Blasius equation can be derived without knowing anything about boundary layers, right? So that means if I non-dimensionalize things appropriately, so phi, if I non-dimensionalize it with something, right? For example, here I think so you can do the math we did last lecture to find out what is the non-dimensionalizing coefficient. So phi has this unit, and basically we need to let me write down what is the unit of nu over theta. Nu over theta is going to be this divided by 1 over L, so it's L cubed divided by T, right? So in order for me to non-dimensionalize phi, which is L squared over T, what do we need? So we have theta. So okay, so let's. So I think we need a combination of this and this, right?
Yeah, to get rid of time.
To get rid of what? So right, I think we can. If we multiply this and UE, we get L to the 4th over T squared. Taking the square root, we get the unit of phi, right? So I think the appropriate non-dimensionalization is nu over theta times UE, right? So this can be written as a function of eta, where eta is defined as, now we need to non-dimensionalize y, which is just the L. And again, we need to take just a combination of this and this. And in this case, dividing them is the good idea, right? Dividing them, we get L. And taking square root, we get... so dividing them, we get L squared. Taking square root, we get L. So nu over theta UE. Right? So now, here we have all the appropriate non-dimensionalizing coefficient to get the Blasius equation. Any questions in this whole derivation? So basically, when we substitute all these, so let's define this to be f, right? When we put all this non-dimensionalization into this equation, into this dimensional equation, why is that? Into this non-dimensional equation, what we get is f. Let's see. So we have minus theta is gone, phi becomes f, and the second derivative of f would be equal to nu is going to be gone, the third derivative of f. So this is the equation we will end up solving, and this is basically the Blasius equation.